What if everything we think we know about the universe is just the tip of an unfathomable iceberg? Picture this: a signal so powerful, so bizarre, it burst through the cosmos in 1977. A blip of radio waves so intense scientists scrawled, "Wow," in red ink across the data printout. Decades later, we still have no idea what caused it. That's the thing about space-time. The deeper we look, the stranger it gets. Black holes that defy physics, galaxies spinning too fast, voids so vast they shouldn't exist. Our universe is littered with glitches, cosmic errors that whisper of layers of reality we can't yet comprehend. And that's just the beginning. For every mystery we've named: dark matter, quantum entanglement, the Fermi Paradox, there are dozens more lurking in the shadows, anomalies that crack the facade of our understanding like fissures in a frozen lake. Some are subtle, detectable only through the slight wobble of a star or the unaccounted weight of a galaxy. Others are impossible to ignore, like the Great Attractor, a gravitational anomaly dragging entire clusters of galaxies toward it at millions of miles per hour. What force could wield that kind of power? The truth is, we're still fumbling in the dark, piecing together a puzzle where half the pieces might belong to a different game entirely. But that's what makes this journey so thrilling. Today, we're diving headfirst into 25 of the most baffling, spine-tingling anomalies in space-time phenomena that twist the rules of reality as we know them. From stars that vanish without a trace to regions where time itself seems to stutter, these aren't just scientific curiosities. They're clues, breadcrumbs left by a universe that's far weirder, far more alive than we ever dared to imagine. So buckle up. By the time we're done, you'll never look at the night sky the same way again. Let's start with the anomaly that sparked a million questions: the WOW signal. On August 15, 1977, a radio telescope in Ohio picked up something extraordinary. A burst of radio waves so strong it dwarfed the usual cosmic background noise. For 72 seconds, this signal blared from the constellation Sagittarius, matching the exact frequency scientists theorized an extraterrestrial transmission might use. Then silence. When astronomer Jerry Amon saw the data printout, he circled the strange code in red ink and scribbled "Wow" next to it, giving the signal its legendary name. Decades later, we're still no closer to solving the mystery. Some argue it was a natural event, maybe a comet's hydrogen emission or a distant star's freak radiation burst. But here's the catch: no known celestial object behaves this way. The signal was narrow, intense, and eerily targeted, characteristics that don't line up with any cosmic phenomena we've observed before or since. Others wonder if it was a fleeting message from an advanced civilization, a cosmic hello sent across the void before vanishing without a trace. The real kicker: despite countless searches, we've never heard anything like it again. It's as if the universe whispered a secret and then clammed up. Even today, the WOW signal taunts us, a tantalizing hint that we might not be alone, or proof that space still holds echoes of forces we don't yet understand. Either way, it's a humbling reminder: some cosmic glitches refuse to be neatly explained. If the WOW signal left you questioning what else is out there, get ready for an even bigger cosmic head-scratcher: dark matter. Imagine holding a snow globe. You can clearly see the flakes swirling inside, but no matter how hard you shake it, nearly 90% of the snow is completely invisible. That's essentially the predicament astronomers face with our universe. Galaxies spin so fast that, according to the laws of physics, they should fling themselves apart. And yet they don't. Something unseen, something massive, is holding them together with an invisible gravitational grip. We call this mystery dark matter, and it's everywhere. In fact, it makes up roughly 27% of the entire universe, outnumbering the atoms in stars, planets, and everything we can see by a factor of 5 to 1. But here's the kicker: despite decades of searching, we still have no idea what it is. It doesn't emit light. It doesn't absorb or reflect it. The only reason we know it exists at all is because it tugs on the things we can see, bending starlight like a lens and warping the very fabric of space-time. So what could it be? Scientists have two leading suspects. The first are WIMP, weakly interacting massive particles, hypothetical heavy particles that barely interact with normal matter except through gravity. Then there are actions, ultra-lightweight particles so elusive they could pass through a mile of lead without a single collision. The problem, despite sophisticated detectors buried deep underground and even in space, we've yet to catch either in the act. Some theorists have even proposed wilder ideas that dark matter might be primordial black holes left over from the Big Bang, or particles from a hidden mirror universe coexisting alongside ours. But until we crack this cosmic case, one thing's for certain: the universe is far stranger than it appears, and the answers we're searching for might rewrite physics as we know it. Just when you thought dark matter was the universe's ultimate enigma, along comes its even more elusive counterpart, dark energy. Picture this: not only is the cosmos expanding, but that expansion is speeding up, as if some invisible hand is pressing harder on the gas pedal with every passing second. And here's the twist: whatever's causing it makes dark matter seem almost straightforward by comparison. The story of dark energy's discovery reads like a cosmic detective novel. In the late 1990s, two teams of astronomers were studying distant supernovae, the colossal explosions of dying stars. These stellar fireworks should have acted like cosmic mile markers, helping measure how fast the universe was expanding. But something was off. The light from these supernovae was fainter than expected, suggesting they were farther away than the math predicted. The only explanation: the space between galaxies wasn't just growing, it was stretching faster and faster over time. The revelation was so shocking, scientists initially double-checked their instruments, convinced there must be a mistake. There wasn't. The universe, it seemed, was being pushed apart by an unseen force, one that dwarfed even gravity's pull. So what is dark energy? The short answer: we have no idea. The leading theory pins it on something called the cosmological constant, a term Einstein once scribbled into his equations as a fudge factor before calling it his greatest blunder. Turns out he might have been right all along. This constant could represent the energy of empty space itself, a kind of anti-gravity woven into the fabric of reality. But here's where things get weird. When physicists calculate how strong this energy should be based on quantum theory, their numbers overshoot observations by a factor of 1 followed by 120 zeros. It's the largest mismatch between prediction and reality in all of science. Alternative theories abound. Maybe dark energy isn't constant at all, but a shifting field that's thinning out or evolving over time, a notion that raises terrifying questions about the universe's ultimate fate. Could it one day rip apart galaxies, even atoms? Or perhaps we're seeing the fingerprints of extra dimensions, or evidence that our understanding of gravity is fundamentally flawed. Whatever the truth, one thing's certain: dark energy isn't just another mystery. It's a glaring reminder that the universe operates on rules we've only begun to glimpse, and that the greatest discoveries might still lie in the shadows, waiting to shatter everything we think we know. But if the universe is so vast and ancient, where is everyone? That's the heart of the Fermi Paradox, one of the most unsettling questions in astronomy. Think about it: with hundreds of billions of galaxies, each containing hundreds of billions of stars, the math suggests intelligent life should be as common as sand on a beach. And yet, our radio telescopes hear only silence. Our sky remains stubbornly empty of alien megastructures or interstellar hello messages. Even our robotic probes scanning Mars or Saturn's moons find no fossils, no ruins, not even a single microbe waving back. So why the cosmic quiet? One terrifying possibility is the Great Filter, some invisible wall that crushes civilizations before they can spread across the stars. Maybe it's the leap from single-celled life to complex organisms, a fluke so rare Earth got lucky. Or perhaps it's self-destruction, nuclear war, runaway AI, or climate collapse acting as a universal graveyard marker. The chilling part, we don't know if we've already passed the filter, or if it's still ahead of us waiting. Then there's the zoo hypothesis, the idea that advanced civilizations are out there, but they're deliberately avoiding us, treating Earth like some galactic nature preserve. It sounds like sci-fi, but consider, would we shout at ants digging their hills, or worse, what if we're the ants and everyone else is communicating in ways we're too primitive to perceive? Other theories get even wilder. Maybe spacefaring cultures inevitably upload their minds into virtual realities, losing interest in the physical universe. Or perhaps we're alone in this epoch, the first sparks of consciousness in a young cosmos still waking up. Whatever the truth, the Fermi Paradox isn't just about aliens. It's a mirror forcing us to ask, are we special or are we doomed? And until we find proof one way or another, that question will keep echoing through the emptiness of space. Some cosmic mysteries lurk in the far reaches of the solar system, and few are as perplexing as the strange case of the Pioneer spacecraft. Launched in the early 1970s, Pioneer 10 and 11 were humanity's first emissaries to the outer planets, destined to become the earliest man-made objects to leave our solar system entirely. But as these trailblazing probes ventured beyond Saturn, scientists noticed something bizarre: their trajectories were off. Despite meticulous calculations accounting for every gravitational pull and cosmic nudge, both spacecraft were slowing down more than they should have. Not by much, just a fraction of a nanometer per second squared, but over decades and billions of miles, even the tiniest discrepancy adds up. By the time Pioneer 10 crossed the orbit of Pluto, it had fallen hundreds of thousands of miles behind where it should have been. This bizarre deceleration became known as the Pioneer anomaly, and for nearly 30 years it defied explanation. At first, researchers suspected mundane causes. Maybe heat radiating unevenly from the spacecraft's nuclear power sources was nudging them off course, or perhaps fuel leaks were creating tiny thrusts in the wrong direction. But after painstaking analysis, none of these theories fully matched the data. The deceleration was too consistent, too precise, as if some unseen force were gently tapping the brakes on humanity's first interstellar messengers. That's when the wilder theories emerged. Could it be evidence of dark matter's gravitational tug, or a flaw in our understanding of gravity itself? Some physicists even toyed with the idea of modified inertia, suggesting that the rules of motion might change ever so slightly in the deep emptiness of space. For a while, the Pioneer anomaly became a rallying cry for those convinced that Einstein's relativity wasn't the final word on cosmic mechanics. Then, in 2012, a team of researchers claimed to have cracked the case. After reconstructing Pioneer 10's heat signature down to the watt, they concluded that thermal radiation was to blame, not as a steady push, but as a subtle, asymmetric glow from the spacecraft's electronics, acting like a faint reverse thruster. Case closed, not quite. While most scientists accept this explanation, lingering questions remain. The heat model doesn't perfectly account for Pioneer 11's drift, and some argue the numbers still don't add up. So was it just a thermal quirk, or did we glimpse something deeper, a shadow of physics yet to be discovered? The pioneers, now silent and drifting toward the stars, carry that secret with them. Their anomaly may be fading from the textbooks, but it stands as a humbling lesson. Even in our own cosmic backyard, the universe still has a few tricks up its sleeve. Fast radio bursts are the universe's most enigmatic whistleblowers, blips of energy so intense they outshine entire galaxies, yet so fleeting they're over before you can blink. Imagine a cosmic strobe light flashing just once, releasing as much energy in a millisecond as the sun does in 3 days, then vanishing without a trace. That's the essence of an FRB. First discovered in 2007, these radio pulses arrive from billions of light years away. their origins shrouded in a fog of theories as wild as the bursts themselves. What makes FRBs so baffling isn't just their power, it's their capriciousness. Some burst once and never repeat, like a car backfiring in the cosmic void. Others fire off sporadically, teasing astronomers with unpredictable encores. In 2020, researchers even caught one inside our own galaxy, erupting from a highly magnetic neutron star known as a magnetar. Finally, a smoking gun, not quite. While magnetars can indeed produce FRBs, they can't explain the most distant energetic bursts. It's like blaming firecrackers for a supernova. So what's really behind these interstellar sirens? The leading suspects are extreme celestial objects, colliding neutron stars, black holes shredding their companions, or exotic phenomena like cosmic strings, defects in space-time left over from the Big Bang. Then there's the zaniest theory, one that even scientists grudgingly acknowledge. Could FRBs be power beams from alien megastructures, propulsion systems for spacecraft the size of planets? It's a fringe idea, sure, but when the cosmos throws a puzzle this strange, every possibility deserves a glance. The real breakthrough came with FRB 121102, the repeater. Located in a dwarf galaxy 3 billion light-years away, this burst has flared up hundreds of times, its rhythm chaotic yet oddly familiar. Some detect patterns in its emissions, whispers of order amid the noise. Others argue it's just cosmic static, the universe's way of keeping us guessing. One thing's certain, every new burst peels back another layer of the mystery, proving space isn't just vast, it's alive with phenomena we're only beginning to decode. Here's the kicker, FRBs might be more than cosmic curiosities. Their signals, stretched and distorted by the intergalactic medium, act like sonar pings through the universe's hidden matter. They're mapping the invisible, probing the cosmic web in ways no telescope can. So while we chase their origins, these bursts are already working overtime, unlocking secrets about the very fabric of space itself. Whether natural or engineered, one truth remains. In a universe that often feels silent, FRBs are screaming for our attention, and we're finally starting to listen. If the universe is meant to be a chaotic, directionless expanse, someone forgot to tell the cosmic microwave background. Stretching across the sky like a fossilized glow from the Big Bang itself, the CMB should be uniform, a speckled tapestry of hot and cold spots with no preferred orientation. But in 2006, astronomers staring at data from the Wilkinson Microwave Anisotropy probe made an unsettling discovery. The universe has a spine. Dubbed the axis of evil by a scientist with a flair for dramatic nicknames, this bizarre alignment shows large swaths of the CMB mysteriously coordinated along a particular plane, as if the cosmos were subtly tipping its hat to some unseen structure. The implications are staggering. The cosmological principle, a cornerstone of modern astronomy, states that the universe should look roughly the same in all directions, no special places, no cosmic center. Yet here we are, staring at a pattern that defies that very idea. Some researchers argue it's just a statistical fluke, a cosmic mirage in the noise. After all, when you're mapping something as vast as the CMB, someone's bound to find odd shapes like seeing faces in clouds, but the axis refuses to vanish. Subsequent studies, including data from the Planck satellite, reinforced the anomaly. The alignment isn't just a quirk, it's persistent, stretching across billions of light-years. So what could be bending the universe's blueprint? One radical theory suggests an ancient gravitational tug from a neighboring universe, a relic from before the Big Bang. Others propose a flaw in our understanding of inflation, that hyper-fast expansion thought to have smoothed the early cosmos. Maybe it didn't erase all wrinkles after all. Then there's the truly mind-bending idea that we're seeing the imprint of something outside our observable universe, a structure so vast its gravity warps reality itself. Mainstream cosmology isn't ready to abandon the cosmological principle just yet. critics point to instrumental errors or overlooked biases in data analysis. But if the axis is real, it's not just an anomaly, it's a crack in the foundation of modern physics. The irony, the very radiation we use to study the universe's infancy might be revealing its best-kept secret, that even in its vastness, the cosmos still has a preferred direction. And that, more than anything, keeps scientists awake at night. Among all the cosmic oddities we've catalogued, few stars have sparked as much debate or wild speculation as KIC 8462852, better known as Tabby's star. Nestled in the constellation Cygnus, this seemingly ordinary star behaves like nothing else in the heavens. Most stars flicker gently as planets pass in front of them, casting predictable, rhythmic shadows. But Tabby's star, it dims erratically, sometimes by as much as 22%, as if something colossal and misshapen is drifting across its face. And then, just as mysteriously, it brightens again. The saga began in 2015 when citizen scientists sifting through data from NASA's Kepler telescope flagged the star's bizarre light patterns. Astronomer Tabby, who led the team studying it, initially chalked it up to a swarm of comets, thousands of them, maybe blotting out the star's light in chaotic waves. But there was a problem. Comets don't explain the sheer scale of the dimming. For a star as massive as Tabby's, you'd need a ridiculous number of comets, far more than any system should naturally harbor. That's when things got interesting. Enter the Dyson sphere hypothesis, the idea that an advanced civilization might build a colossal energy-harvesting megastructure around their star, capturing its power with a lattice of orbiting panels. The irregular dimming, just sections of this alien construct passing in front of the star. It's a sci-fi dream, but for a brief moment it seemed plausible. Even the search for extraterrestrial intelligence trained its antennas on Tabby's star, listening for the telltale hum of alien technology. They heard nothing. Yet the mystery only deepened. Subsequent studies revealed something even stranger. Tabby's star isn't just dimming erratically, it's fading overall. Between 1890 and 1989, its brightness dropped by 14%. Stars this massive don't just quietly fizzle out over a century. So what's stealing its light? Dust seems the likeliest culprit. In 2018, researchers noticed the dimming was more pronounced at shorter wavelengths, a hallmark of fine cosmic dust scattering starlight. But where's the dust coming from? A catastrophic planetary collision, a disintegrating moon. Even now, no single theory fits all the data. Here's what makes Tabby's star so thrilling. It's a reminder that nature is stranger than fiction. Whether it's a swarm of broken planets, a cosmic dust factory, or just maybe something beyond our current understanding, this star refuses to fit into neat boxes. Every time we think we've solved it, it throws us another curveball, daring us to look deeper. And that's the beauty of cosmic anomalies. They don't just challenge our models. They challenge our imagination. Deep in the cosmic shadows, where the Milky Way's dense starlight blinds our telescopes, lurks something massive enough to bend the paths of entire galaxies like a cosmic puppeteer. Meet the Great Attractor, a gravitational anomaly so powerful it's dragging our local supercluster, along with thousands of other galaxies, toward it at a staggering 14 million miles per hour. And here's the kicker, we can't even see what's pulling us. The mystery begins with the so-called zone of avoidance, a region of space obscured by the Milky Way's own dust and stars. Imagine trying to peer through a snowstorm while standing in the middle of it. That's the challenge astronomers face when studying this patch of sky. But in the 1970s, as scientists mapped the motions of nearby galaxies, they noticed something eerie. Everything was flowing in the same direction, as if caught in a river no one could see. The Great Attractor wasn't just a curiosity. It was a gravitational wake-up call, proof that even on the grandest scales, the universe was anything but random. For decades, researchers pieced together clues like cosmic detectives. infrared and radio telescopes capable of piercing the Milky Way's veil revealed clusters of galaxies in the attractor's general vicinity, but not nearly enough to account for its pull. The math just didn't add up. Then came an even bigger revelation. The great attractor itself might be a mere waypoint. Beyond it lies something far more colossal, the Shapley supercluster, a gargantuan knot of matter 800 million light-years away, its gravity weaving an invisible web that tugs on everything in our corner of the cosmos. Yet the puzzle isn't solved. Recent studies suggest the attractor's influence extends even farther, intertwined with the mysterious dark flow, a controversial observation that some galaxies are drifting toward an unseen structure beyond the observable universe. Could it be the gravitational echo of another universe brushing against ours, or evidence of a flaw in our understanding of how matter clumps together? One thing's certain, the Great Attractor is more than a scientific oddity. It's a humbling reminder that even as we map the cosmos, the most influential forces might still be hiding in plain sight or just beyond it. Every new observation peels back another layer, revealing a universe far more connected and far stranger than we ever imagined. If the universe has a rulebook, quantum entanglement scribbles all over it in neon ink. Picture two particles born from the same event, spinning in perfect sync like synchronized dancers. Now fling them to opposite ends of the galaxy. According to quantum mechanics, if you tweak one, say, flip its spin, the other instantly mirrors that change, no matter how far apart they are. No signal passes between them, no force travels the distance. It's as if space-time itself is just a suggestion, and these particles are playing by a different set of rules entirely. Einstein famously hated this idea, calling it spooky action at a distance. To him, it violated relativity's sacred law: nothing can outrace light. How could information zip between particles faster than a photon's speed limit? For decades, physicists argued whether entanglement was real or just a quirk of math. Then, in the 1970s, a thinker named John Bell devised an experiment to settle the debate. The results were unequivocal. Entanglement wasn't a glitch, it was built into the fabric of reality. Here's where things get wild. Entanglement doesn't just defy intuition, it shreds our classical notions of space and time. Imagine two coins that always land on opposite sides, even if one's in New York and the other on Mars. That's child's play compared to what happens in quantum labs today. Researchers have entangled particles across hundreds of miles, even beaming them via satellite to prove the effect holds. The particles don't just communicate, they exist in a shared state, as if the universe forgets they're separate entities until someone looks. So what's really going on? One mind-bending explanation is that entangled particles aren't truly connected at all. Instead, they might be accessing a deeper layer of reality where distance is an illusion, a concept called non-locality. Think of it like two actors performing a play. Their lines match perfectly not because they're whispering cues, but because they're following the same unseen script. The implications are staggering. If entanglement holds at cosmic scales, it could hint at a universe knit together by hidden threads, where separation is just a surface-level illusion. Some theorists even suggest this might be the key to quantum gravity, bridging the gap between the tiny quantum world and the vast stretches of relativity. Others dream of quantum internet, ultra-secure networks where information hops between nodes instantly, no cables required. Yet for all its promise, entanglement remains stubbornly enigmatic. We can use it without fully understanding it, like cavemen harnessing fire before knowing about atoms. Every experiment peels back another layer, revealing a cosmos far more interconnected and far stranger than Einstein ever feared. And that's the real spookiness. The universe might not just be weird, it might be weirder than we're capable of imagining. Black holes aren't just cosmic vacuum cleaners, they're the ultimate shredders of reality. According to Einstein's general relativity, once something crosses a black hole's event horizon, it's gone forever. crushed into a singularity where space and time cease to make sense. But here's the problem. Quantum mechanics, the rulebook for the subatomic world, insists that information, the story of every particle, can never truly be destroyed. This clash isn't just academic, it's a battle for the soul of physics, and it's called the black hole information paradox. The fuse for this cosmic debate was lit in the 1970s by Stephen Hawking himself. He theorized that black holes aren't entirely black. Thanks to quantum fluctuations at the event horizon, they slowly leak energy, a phenomenon now called Hawking radiation. Over eons, this drip feed of particles causes black holes to evaporate entirely, vanishing like smoke. But here's the catch. Hawking's math suggested the radiation carried no information about what fell in. All those swallowed stars, planets, and particles, their histories would be erased from the universe, violating quantum mechanics' sacred law of information conservation. Cue decades of scientific panic. If Hawking was right, our understanding of reality was fundamentally broken. Physicists split into warring camps. Some clung to the idea that information was truly lost, rewriting quantum theory to accommodate it. Others, like Leonard Susskind, fought back with the holographic principle, a radical notion that all the data swallowed by a black hole isn't destroyed but smeared across its event horizon like a cosmic DVD, encoded in tiny Planck-scale pixels. Then, in 2016, Hawking himself, along with colleagues Malcolm Perry and Andrew Strominger, proposed a twist. Maybe information does escape, hidden in soft hairs, ultra-low-energy particles lingering near the event horizon. It was a tantalizing clue, but critics argued these hairs were too faint to carry the full story. The paradox refused to die. The real bombshell came in 2019, when a team calculated that Hawking radiation might preserve information after all, scrambled like a cosmic cryptographic puzzle. Even more startling, recent experiments with quantum analog black holes, created in labs using sound waves or light, hint that information could indeed survive, entangled in ways we're just beginning to map. So where does this leave us? On the brink of a revolution. Solving the paradox could unlock quantum gravity, the holy grail of physics, merging Einstein's cosmos with the quantum realm. It might reveal that black holes aren't tombs but translators, transmuting matter into some new form we've yet to comprehend. Or just maybe it'll force us to rewrite the textbooks entirely, admitting that the universe keeps its deepest secrets hidden even from the brightest minds. One thing's certain, when it comes to black holes, the only paradox is thinking we've got them figured out. Imagine a bubble in the universe so vast you could fit 60 Milky Way galaxies across it, and inside almost nothing. That's the Boötes void, a cosmic desert spanning 330 million light-years where galaxies should be crowding like skyscrapers in a city. Instead, it holds just 60 or so lonely galaxies adrift in an ocean of darkness. To put that in perspective, if the universe were a bustling metropolis, the Boötes void would be a ghost town the size of a continent. Discovered in the 1980s during a galaxy survey, this void wasn't just unexpected, it was impossible by most cosmological models. The Big Bang's afterglow shows a universe speckled with dense clusters and wispy filaments, a cosmic web where matter clumps together like foam. Yet the Boötes void is a hole punched through that web, a place where the rules of structure seem to have been forgotten. So how does a chunk of space this big end up so empty? One theory points to inflation, that split-second hyper-expansion right after the Big Bang. Tiny quantum fluctuations might have stretched into vast bubbles, some overdensities becoming galaxy clusters, others underdensities ballooning into voids. But even this can't fully explain the Boötes void's extreme barrenness. It's like finding a swimming pool in the middle of a rainforest. Nature just doesn't tend to work that way. Then there's the darker, wilder idea. What if the void isn't natural at all? Some theorists half-jokingly, half-seriously, floated the notion of a Type 3 civilization, a galactic empire so advanced it could harvest the energy of entire galaxies, leaving behind a hollowed-out shell. It's a tantalizing thought, but Occam's razor slices it down. The void's few galaxies show no signs of engineering, and the energy required to clear such space defies even hypothetical physics. Yet the Boötes void's real mystery isn't just its emptiness, it's the eerie way its few galaxies are arranged. Instead of scattered randomly, they cluster along faint, thread-like structures, as if clinging to the last ropes of a sinking ship. This hints that the void might not be a perfect sphere of nothingness, but a complex, evolving structure, its edges slowly eroding as gravity pulls matter inward from the surrounding cosmic web. New telescopes like the Vera Rubin Observatory may finally shed light on this enigma, mapping the void's faintest galaxies in unprecedented detail. Until then, the Boötes void stands as a cosmic Rorschach test, a blank canvas inviting us to project our wildest theories onto it. Whether it's a relic of the universe's birth, a statistical fluke, or something stranger, one thing's certain: in a cosmos teeming with matter, emptiness this profound isn't just a gap. It's a screaming anomaly. While the Boötes void leaves us baffled by its sheer emptiness, there's another cosmic blank spot that raises even thornier questions: the Eridanus supervoid. Unlike its cousin, this void isn't just a gap in galaxy distribution. It's a chilling cold spot stamped across the cosmic microwave background, the afterglow of the Big Bang itself. Picture pressing your hand against a foggy mirror. The mark you leave is the Eridanus supervoid, a cosmic fingerprint so vast and cold it defies easy explanation. The cold spot was first spotted in 2004 by NASA's a Wilkinson microwave anisotropy probe, and it's not your average statistical blip. While the CMB is peppered with tiny fluctuations, this region is 7 times colder than expected, stretching over 1 billion light-years. At first glance, you might think it's just another void, a sparse patch of space where fewer galaxies mean less energy, cooling the CMB. But here's the catch: the Eridanus supervoid, while gigantic, isn't nearly empty enough to account for such a dramatic temperature drop. It's like opening your freezer to find a glacier inside. Something's not adding up. That's where the theories get wild. One camp argues it's a statistical fluke, a cosmic mirage created by overlapping smaller voids. After all, in a universe this vast, even the rarest anomalies might pop up by chance, but the odds less than 2%, say some calculations. Others propose a far more radical idea: the cold spot might be a bruise from a collision with another universe. In multiverse theories, bubbles of spacetime can bump against each other, and the energy drain from such a collision could leave behind a cold imprint. It's a stretch, sure, but when conventional physics falls short, scientists start eyeing the unconventional. Then there's the dark horse explanation: a defect in the very fabric of space-time. Cosmic strings, hypothetical, thread-like cracks in reality left over from the universe's birth, could theoretically warp the CMB around them, creating localized cold zones. Or perhaps the cold spot is a shadow cast by some immense, unseen structure lurking beyond our observable horizon. The debate rages because the stakes are cosmic. If the Eridanus supervoid is just a fluke, it's a reminder of how randomness shapes the universe. But if it's a window into the multiverse, that rewrites everything. New telescopes like the Simons Observatory are training their sights on this enigmatic patch, hunting for clues hidden in its faintest whispers. Until then, the cold spot remains a cosmic Rorschach test, freezing us in place, daring us to see patterns in the frost. The Moon, our silent celestial companion, holds a secret that upends everything we thought we knew about planetary magnetism. Today, it's a barren rock with no global magnetic field, but billions of years ago, lunar rocks tell a different story. Samples brought back by Apollo astronauts contain traces of magnetism, evidence that the Moon once had a magnetic shield rivaling Earth's. Here's the problem: magnetic fields usually require a churning molten core like Earth's iron dynamo. But the moon is too small, too cold. It should have lost its heat and solidified eons ago. So how did it generate this ancient field? Scientists call it the lunar dynamo puzzle, and it's one of the solar system's most stubborn riddles. For decades, the leading theory pointed to sheer brute force. Perhaps the moon's core stayed molten longer than expected, stirred by the gravitational tug of war with Earth. Early in its history, the moon orbited much closer, and that stretch and squeeze could have kept its core bubbling like a pot on simmer. But computer simulations delivered a harsh reality check. Even under extreme conditions, the moon's core would have cooled within 100 million years. Yet the Apollo rocks tell us its magnetic field persisted for over 1 billion years. Something doesn't add up. That's when researchers started eyeing wilder explanations. One suggests the moon's crust played an unexpected role. Imagine massive asteroid impacts not just pebbles, but planet-shaking collisions melting the moon's outer layers. These molten oceans could have swirled with electrically charged material, temporarily fueling a magnetic field like a cosmic battery. There's even evidence supporting this. Some of the strongest magnetic traces in lunar rocks align with the timing of ancient mega-impact. But critics point out that such fields would be patchy, not the global shield the moon seems to have maintained. Then there's the precession theory. Picture a spinning top wobbling as it slows. That's precession. Early in its life, the moon may have wobbled dramatically, sloshing its core like coffee in a mug. This motion could have generated a dynamo effect without requiring constant molten heat. Recent models show promise, but they still struggle to explain how the field lasted so long. Perhaps the most radical idea, the moon's core wasn't just iron. If it contained lighter elements like sulfur, they could have acted like antifreeze, keeping the core simmering far longer than pure metal allows. Some lab experiments back this up, showing sulfur-rich alloys stay molten under lunar conditions. But until we send new missions to drill deeper into the moon's history, we're left with a celestial whodunit. The stakes are higher than just lunar trivia. If small, rocky bodies like the moon can sustain magnetic fields against the odds, it rewrites the playbook for exoplanets. Could lifeless worlds we've dismissed as too cold or too small harbor hidden dynamos, and with them the potential to shield atmospheres or even life? The moon's magnetic ghost whispers that the universe might be full of surprises, hiding in the last places we'd think to look. Saturn's North Pole looks like something out of a cosmic geometry textbook, a perfect, swirling hexagon spanning 20,000 miles, wide enough to fit 4 Earths side by side. This six-sided storm has raged for at least 4 decades, possibly much longer. Its razor-sharp edges defying every expectation of how fluids behave in nature. Earth's hurricanes, chaotic blobs, Jupiter's great red spot, a shapeless vortex, but Saturn's hexagon. It's so precise, it's as if the planet hired an architect. The first hints of this anomaly came in the 1980s, when Voyager spacecraft glimpsed the structure during flybys. Scientists dismissed it as a fleeting oddity, until Cassini arrived in 2004 and found it still there, unchanged like a celestial tattoo. Time-lapse images revealed the hexagon's walls as towering jets racing at over 200 miles per hour, with smaller vortices pirouetting at its corners like dancers locked in a cosmic waltz. Yet despite this violence, the shape holds, its angles never softening, its pattern never fraying. So how does a storm this stable exist? Fluid dynamics offers clues. On Earth, atmospheric patterns are messy, shaped by friction from mountains and oceans, but Saturn is a gas giant, no solid surface to disrupt the flow. In lab experiments, spinning fluids can form polygons if the outer layer moves faster than the core. Tweak the speed just right, and turbulence self-organizes into geometric shapes. Some models suggest the hexagon is a standing wave, a traffic jam in Saturn's jet streams where winds pile up into stationary peaks and troughs. Others propose it's the fingerprint of deep-rooted convection, like bubbles rising in a boiling pot but scaled to planetary proportions. Yet even these explanations feel incomplete. Why a hexagon? Why not an octagon or a pentagon? The number 6 might be a resonance effect, a mathematical sweet spot where competing forces balance. Or perhaps it's tied to Saturn's bizarre magnetic field, which oddly aligns almost perfectly with its rotation axis, unlike Earth's tilted magnetism. The hexagon could be a surface ripple from some deeper, unseen turbulence, like the wake of a submarine we can't detect. What truly boggles the mind is that nothing like this exists anywhere else we've looked. Not on Jupiter, not on Neptune, not even in supercomputer simulations of hypothetical exoplanets. Saturn's hexagon is a cosmic unicorn, a reminder that even the laws of physics can sculpt surprises when given the right or wrong ingredients. Maybe that's the real lesson here. In an infinite universe, even the impossible might just be waiting for the perfect conditions to reveal itself. As if the cosmos were deliberately taunting us with riddles, in October 2017, astronomers spotted something streaking through our solar system that defied all expectations. A slender, tumbling object moving too fast to be bound by the sun's gravity. Named Oumuamua Hawaiian for Scout, it was the first confirmed visitor from interstellar space, and it left scientists scrambling to explain its bizarre traits. For starters, its shape was unlike any asteroid or comet we'd seen. Radar measurements suggested an elongated, cigar-like form, stretching perhaps 600 feet long but only a tenth as wide, a cosmic needle tumbling end over end. Natural objects simply don't look like that. Most space rocks are lumpy potatoes, not geometric oddities. Then came the real shock. Oumuamua accelerated as it departed the inner solar system, as if propelled by an unseen force. Comets do this when sunlight vaporizes their ice, creating a faint thrust, but Oumuamua showed no coma, no tail, no dusty exhaust. It was speeding up in silence. Cue the scientific scramble. Mainstream theories pointed to exotic but natural explanations. Maybe Oumuamua was a hydrogen iceberg, a chunk of frozen molecular hydrogen shedding invisible gas as it warmed. Hydrogen doesn't glow like water vapor, so we wouldn't see a tail. Problem is, hydrogen ice is notoriously fragile. It's unclear how such an object could survive a journey across light years without evaporating. Others suggested it was a fractal-like dust aggregate, a cosmic tumbleweed so porous it reflected light strangely, fooling our instruments about its shape. But when Harvard astrophysicist Avi Loeb floated the idea that Oumuamua might be artificial, a light sail or derelict probe from an alien civilization, the internet lost its collective mind. Loeb noted its acceleration matched what a thin, reflective sheet pushed by starlight might achieve. No, he wasn't claiming proof of ET, just highlighting how poorly our models fit the data. The backlash was swift. Critics dismissed it as sensationalism, arguing extraordinary claims require extraordinary evidence, and Oumuamua's quirks, while weird, weren't definitive. Yet the debate revealed a deeper truth. Sometimes anomalies expose the limits of our imagination. We're so wedded to familiar categories, comets, asteroids, that we forget the universe might craft objects we've never dreamed of. Oumuamua could be a shred of a Pluto-like world torn free in some ancient collision, or a remnant of a rogue planet's shattered crust, or yes, something stranger. The real tragedy we'll likely never know. By the time we spotted Oumuamua, it was already racing away, too faint for further study. It's now beyond Pluto's orbit, vanishing into the dark. Unless another interstellar guest drops by, preferably slower, and with clearer clues, this cosmic enigma will remain just that, a fleeting whisper from the void, challenging us to wonder what else might be sailing unseen through the starry sea. In the grand cosmic ledger, there's a number so crucial it might just unravel our understanding of the universe itself. The Hubble constant, the rate at which space is stretching apart. For decades, astronomers assumed this expansion was a steady drumbeat, a single value etched into the fabric of reality. but in recent years something peculiar has emerged, a glaring mismatch between how fast the universe should be growing and how fast it actually is. Scientists call it the Hubble tension, and it's not just a minor accounting error. It's a full-blown crisis in cosmology. The plot thickens when you realize we have two impeccable ways to measure this expansion. The first involves peering back to the universe's infancy, using the cosmic microwave background, that fossilized glow from the Big Bang. By studying subtle ripples in this ancient light, scientists can calculate how fast space started expanding, then project forward to today. The second method skips the history books and looks at modern stars, particularly dying ones called Type 1a supernova. These stellar explosions are so predictable they're called standard candles, letting astronomers gauge distances across the cosmos. Here's where the tension snaps. The CMB method, championed by the Planck satellite, suggests the universe is expanding at about 67 kilometers per second per megaparsec. But supernova measurements, including data from Hubble itself, peg the number closer to 73. That gap might seem small, but in the precise world of astrophysics, it's a canyon. Imagine two clocks, one ticking slightly faster than the other. Over a day, no big deal. Over billions of years, the divergence becomes cosmic. So what's behind this rift? One camp argues for hidden errors. Maybe supernova aren't as standard as we thought, or perhaps dust in space is distorting their light. But after years of cross-checking, these wrinkles refuse to smooth out. That's led theorists to eye more radical fixes. Could dark energy, that mysterious force accelerating the universe, be changing strength over time? Or is there an undiscovered particle, like a dark photon, subtly tweaking gravity's rules? Some even speculate we're seeing echoes of a second Big Bang, a colossal event that rewired physics in the universe's first moments. The stakes couldn't be higher. If the Hubble tension is real, if the universe's expansion rate truly depends on when you measure it, then our textbooks are missing a chapter. Maybe space isn't just expanding, maybe the rules of the game are shifting under our feet. New telescopes like the James Webb Space Telescope are now joining the hunt, scrutinizing ancient galaxies and supernova with unprecedented precision. Whatever they find, one thing's certain: the cosmos is keeping secrets, and the Hubble tension might just be the first loose thread in a much larger tapestry of mysteries. The Eridanus supervoid's cold spot isn't just a cosmic anomaly, it's a screaming contradiction plastered across the sky. While most of the cosmic microwave background shimmers with tiny temperature fluctuations, this region is a chilling outlier, a patch of space so cold it's as if the universe left the freezer door ajar. But the real mystery isn't just the cold, it's the sheer scale. Stretching over 1 billion light-years, this void defies every expectation of how matter should clump together. If it were truly just an empty bubble, its gravitational tug should have warmed the CMB, not cooled it. So what's really going on? One faction of cosmologists argues we're staring at a cosmic defect, a scar left over from the universe's birth. Imagine space-time as a sheet of ice forming on a pond. As it freezes, cracks might appear, flaws in the structure. Cosmic strings, hypothetical threads of pure energy thinner than an atom but denser than a neutron star, could be those cracks. If one slices through the Eridanus region, its gravitational pull might warp light in a way that mimics a cold spot. It's an elegant idea, but there's a hitch. No one's ever detected a cosmic string directly, and their existence remains purely theoretical. Then there's the multiverse camp. In this scenario, the cold spot isn't a flaw in our universe, it's a bruise from a collision with another. Picture two soap bubbles bumping in a sink. Where they touch, energy transfers, leaving a dimple. If another universe brushed against ours in the distant past, the energy drain could have left behind this frigid footprint. It's a wild idea, but not without math to back it up. Simulations show such collisions could imprint cold spots, though the odds of one lining up perfectly with a visible void are astronomically low. Skeptics, though, have a simpler explanation. The cold spot might just be a trick of the light. The CMB is a noisy map, and even random fluctuations can sometimes stack up to look significant. Throw in the way our telescopes filter data, and you've got a recipe for phantom patterns. But here's the twist: when researchers removed the void from their models, the cold spot still didn't vanish. That suggests the void and the coldness might be unrelated, a cosmic coincidence that's fooling us into seeing connections where none exist. The battle over the cold spot isn't just academic, it's a proxy war for the soul of cosmology. If it's a defect or a multiverse bruise, it means our universe is stranger than we dreamed. If it's a fluke, it's a humbling reminder that even the cosmos can roll snake eyes. New telescopes like the Simons Observatory are now scanning this frozen enigma, hunting for subtle polarization patterns that could tip the scales. Until then, the cold spot remains a Rorschach test for physicists, a blank slate where they see their deepest hopes, fears, and unfinished equations staring back. The universe isn't just expanding, it's sculpting itself into structures so vast they defy comprehension. Among them, the Hercules Corona Borealis Great Wall stands as a cosmic colossus, a filament of galaxies stretching 10 billion light-years across. To put that in perspective, if our Milky Way were the size of a coffee bean, this wall would span the width of North America. And here's the kicker: according to our best models of cosmology, nothing this big should exist. The cosmological principle, a bedrock of modern astronomy, states that on large scales, the universe should look roughly the same everywhere, no special places, no preferred directions. Yet the Hercules Corona Borealis Great Wall isn't alone. It's part of a rogues gallery of superstructures: the Sloan Great Wall, the Laniakea Supercluster, the South Pole Wall, each one a cosmic quilt stitching together thousands of galaxies into patterns that mock the idea of homogeneity. So how do these behemoths form? The leading theory points to dark matter's invisible scaffolding. In the early universe, tiny density fluctuations, seeds planted by quantum randomness during inflation, grew under gravity's pull, drawing galaxies together like beads on a string. But simulations suggest there's a natural limit to how big these threads can get before the universe's expansion tears them apart. The Hercules Corona Borealis Great Wall shatters that limit. It's not just a thread, it's a cosmic tapestry woven on a loom we don't yet understand. Critics argue these superstructures might be optical illusions, trickery of perspective where unrelated galaxies appear connected. Yet the odds of so many alignments happening by chance are vanishingly small. Others propose a radical fix. Maybe the cosmological principle isn't universal. Could we be living in a rare, over-dense bubble, a cosmic metropolis that skews our view of the wider universe? It's like standing in a dense forest and assuming all of Earth looks the same, unaware of deserts and oceans beyond the trees. The stakes are cosmic. If these walls are real, they hint at forces or initial conditions beyond our standard models, perhaps relics of pre-Big Bang physics, or evidence that dark energy's grip isn't as uniform as we thought. New telescopes like ESA's Euclid are mapping these structures in 3D, probing whether they're true anomalies or just the universe reminding us. Scale is a mirror, and the deeper we look, the smaller our assumptions seem. If black holes are the universe's ultimate shredders, then their hypothetical twins, white holes, are the cosmic staplers, endlessly putting everything back together. Picture a black hole running in reverse. Instead of swallowing matter and light, a white hole would violently spit them out, a fountain of space-time refusing to let anything in. The math allows for this. Einstein's equations, which describe black holes so perfectly, are symmetric. They don't care if time flows forward or backward. Flip a black hole's timeline and voila, you've got a white hole. But here's the rub: while black holes are everywhere, from the centers of galaxies to the aftermath of colliding neutron stars, white holes remain purely theoretical. No telescope has ever caught one in the act of cosmic regurgitation. Some physicists argue they're just mathematical curiosities, artifacts of equations that don't reflect reality. Others think we haven't been looking hard enough or in the right way. The most tantalizing idea comes from loop quantum gravity, a framework trying to bridge Einstein's relativity with quantum mechanics. In this theory, when a black hole dies, it doesn't vanish into a singularity's infinite density. Instead, it rebounds, its collapse reversing into an explosion, a white hole. This process would take billions of years for a typical black hole, meaning the universe might be too young for us to see one yet. But what if some primordial black holes forged in the Big Bang's chaos have already made the switch? Their white hole offspring could be out there now, erupting like geysers in the cosmic dark. Then there's the wild card, gamma-ray bursts. These flashes of high-energy light are some of the most violent events in the universe, often linked to collapsing stars or colliding neutron stars. But a handful defy explanation. Their energy profiles oddly smooth, as if something were filtering the chaos. Could these be white holes' fingerprints? It's a fringe idea, but in a cosmos full of surprises, ruling it out entirely might be premature. The real kicker, if white holes exist, they'd be more than just cosmic oddities. They'd be evidence that space-time itself has a memory, a way to recycle singularities rather than let them be dead ends. That would rewrite our understanding of fate, not just for stars and galaxies, but for the universe itself. For now, white holes remain ghosts in the equations, whispering that the cosmos might still have a few escape hatches we haven't found yet. And that's the beauty of theoretical physics. Sometimes the most outlandish ideas are just waiting for the right moment to reveal themselves. We like to think we've got the universe's inventory figured out: stars, galaxies, gas, and dust, all neatly accounted for. But here's a cosmic accounting error that's been gnawing at scientists for decades. Roughly half the ordinary matter in the universe has gone missing. Not dark matter, that's a whole other mystery, but the protons, neutrons, and electrons that make up everything we can see. These baryons, the building blocks of atoms, should be everywhere, yet when we tally them up, the numbers don't match. Where's the universe hiding them? The first clues to this cosmic shell game came from studying the afterglow of the Big Bang. By measuring the cosmic microwave background's subtle ripples, scientists calculated how much ordinary matter the universe should contain. Then they counted what they could see: stars, galaxies, the glowing gas between them, and came up short, way short. We're talking about enough missing matter to build trillions of Milky Ways vanished without a trace. So if it's not in the obvious places, where is it? Enter the cosmic web, the universe's hidden scaffolding. Picture an enormous spider's silk, invisible until the morning dew clings to it. Astronomers now suspect the missing baryons are tangled in these vast, thread-like filaments of warm, hot intergalactic medium, WIM for short. This isn't the dense, glowing gas of nebulae. It's a diffuse, superheated plasma, so thin and energetic it's nearly transparent. Imagine trying to spot a single light bulb in a foggy city. It's there, but the glare washes it out. Detecting the WIM is like playing cosmic hide and seek with a ghost. Traditional telescopes can't see it directly, so scientists have to get creative. One trick is to watch how the WIM distorts light from distant quasars, those brilliant galactic cores. As the quasar's light passes through these filaments, certain wavelengths get absorbed, leaving faint chemical fingerprints in the spectrum. It's like finding a hidden message written in ultraviolet ink, only visible under the right conditions. Another approach involves hunting for X-rays. At temperatures of millions of degrees, the WIM should emit a faint glow in this high energy range. In 2018, the Hitomi satellite caught a glimpse of this signal in the Perseus galaxy cluster, a wispy emission that matched predictions. But these observations are like catching whispers in a hurricane. The signals are so faint, so easily drowned out by cosmic noise, that confirming them feels like chasing smoke. The real twist: some of these missing baryons might be lurking even closer to home. Simulations suggest our own galactic neighborhood could be swimming in warm hot gas, a sparse but massive halo extending far beyond the Milky Way's visible disk. If true, we've been sitting in the middle of the mystery all along, oblivious to the ocean of particles right above our heads. So why does this matter? Because baryons aren't just cosmic filler, they're the raw material for every star, planet, and living thing in existence. Finding them isn't just about balancing the universe's books, it's about understanding how galaxies form, how structures evolve, and where the next generation of stars might ignite. The hunt for these missing baryons is a reminder that even the ordinary universe still has secrets hiding in plain sight, waiting for us to look just a little harder. If the universe stretches infinitely into space and time, why isn't the night sky blindingly bright? This is the heart of the Tolman paradox, a cosmic riddle that's haunted astronomers for centuries. Imagine standing in an endless forest where every gap between trees is filled with more trees. No matter where you look, your gaze should eventually land on a trunk. Now replace those trees with stars. In an infinite, ageless universe, every line of sight should terminate at a star's surface, painting the entire sky in a searing, uniform glow. And yet, when we look up, darkness reigns. This contradiction, a variation of the classic Olbers paradox, isn't just a thought experiment, it's a profound clue about the nature of reality itself. The paradox gets its teeth from a simple assumption. If the universe is eternal and unchanging, starlight should have had infinite time to reach us, but the night sky's darkness tells us that assumption is flawed. 19th century astronomers like Heinrich Olbers proposed band-aid fixes. Maybe dust blocks distant starlight, but that just kicks the can. Interstellar dust would absorb that energy and eventually re-emit it, heating up until it glowed just as brightly as the stars themselves. The real answer, it turns out, lies in the universe's restless, expanding nature. Edwin Hubble's groundbreaking observations in the 1920s revealed that galaxies are racing apart, stretching space itself like a cosmic loaf of raisin bread. This expansion does two critical things. First, it means the universe isn't static. It had a beginning, a moment when the lights switched on. The Big Bang theory gives us a finite age for the cosmos, roughly 13.8 billion years, so light from stars beyond that horizon hasn't had time to reach us. Second, expansion stretches the very fabric of light waves, shifting visible starlight into infrared or radio wavelengths invisible to our eyes. The universe isn't just hiding stars, it's quietly redacting their light. But the Tolman paradox adds a twist. In the 1930s, physicist Richard Tolman realized that in an expanding universe, light from distant objects doesn't just dim, it loses energy over time. Photons traveling across stretching space get tired, their wavelengths elongating into oblivion. This cosmic redshift acts like a universal dimmer switch, ensuring that no matter how many stars exist, their collective glow will never overwhelm the sky. Modern cosmology takes it further. The universe isn't just expanding, it's accelerating thanks to dark energy. Distant galaxies are fleeing so fast their light may never reach us, leaving vast regions of the cosmos forever unseen. Combine this with the fact that stars aren't eternal, they burn out, collapse, or explode, and the puzzle snaps into focus. The night sky is dark because the universe is dynamic, evolving, and fundamentally finite in what we can observe. The Tolman paradox, then, is more than a clever brain teaser. It's a cosmic breadcrumb trail pointing toward the Big Bang, dark energy, and the universe's impermanence. Every time we gaze at the stars, we're not just looking outward. We're peering backward through time, seeing a sky that's dark not because the universe is empty, but because it's alive, changing, and far stranger than a static infinity could ever be. Physics textbooks will tell you every action has an equal and opposite reaction, Newton's third law, the bedrock of propulsion. But in the late 90s, British engineer Roger Scheuer proposed a device that laughed in the face of that principle, the M-drive, an engine that promised thrust without exhaust. Picture a metal chamber shaped like a truncated cone, buzzing with microwaves bouncing wildly inside. According to Scheuer, this chaotic dance should have generated net thrust out of pure electromagnetic mayhem. No fuel, no exhaust, just a push. The implications were staggering. A spacecraft that could accelerate indefinitely without lugging propellant, cutting interstellar travel times from millennia to decades. At first, the scientific community dismissed it as textbook nonsense. Momentum must be conserved. You can't get thrust from nothing. But then, something strange happened. In 2016, NASA Eagleworks Lab, a skunkworks division testing fringe propulsion ideas, reported detecting tiny but measurable thrust from their own M-drive prototype. Not much, just micronewtons, barely enough to budge a grain of sand, but in the precise world of physics, even a whisper of impossible is deafening. Suddenly, labs in China, Germany, and the UK were scrambling to reproduce the results. Some succeeded, others found nothing. The debate exploded into a full-blown scientific brawl. Critics pounced on flaws in the experiments. Vibrations from Earth's magnetic field could mimic thrust. Thermal expansion of the device as it warmed might nudge measurements. Even the vacuum chambers used for testing weren't perfectly empty. Stray molecules bouncing off the M-drive could create false signals. By 2021, a team at Dresden University put the controversy to bed with an ultra-precise test. Their verdict, the thrust, was just magnetic interference, a classic case of experimental noise masquerading as discovery. Yet whispers linger. Why did some labs detect thrust while others didn't? Could quantum effects we don't fully understand, like interactions between microwaves and virtual particles in the vacuum, play a role? The M-drive's ghost still haunts physics forums and garage workshops, a testament to humanity's hunger for impossible dreams. It's a cautionary tale, too. Sometimes anomalies aren't cracks in reality's foundation, just dust on the lens. But in a universe that constantly defies expectations, who's to say the next impossible engine won't rewrite the rules after all? Look up at the night sky just before dawn or after dusk, and you might catch a faint, eerie glow rising from the horizon, a triangular veil of light stretching along the ecliptic, the path where planets travel. This is the zodiacal light, a phenomenon long attributed to sunlight scattering off cosmic dust lingering in the inner solar system. But here's the puzzle. Recent measurements reveal there's too much light, far more than the known dust in our cosmic neighborhood should produce. It's as if we've been handed a flashlight and told to find the bulb, only to realize the beam is coming from something far stranger than we ever imagined. For centuries, astronomers assumed the zodiacal light was just sunlight bouncing off the debris left behind by comets and asteroids, fine grains drifting in the same plane as Earth's orbit. But when spacecraft like NASA's Juno mission flew through this region, their dust detectors came up shockingly empty. The numbers didn't add up. The glow we see requires about 20 times more dust than we've actually found. So if it's not dust, what's illuminating the darkness? One radical theory points to dark matter. Not the clumps hiding in galaxy halos, but a speculative form called macro-dark matter, particles as hefty as asteroids but invisible to our telescopes. If these unseen chunks are peppering the solar system, they could collide and shatter, releasing fine debris that reflects sunlight just enough to explain the excess glow. It's a long shot, but the math could work. Others suggest we're seeing the ghostly fingerprints of actions, hypothetical particles so lightweight they behave more like waves than matter. Under certain conditions, actions might convert into photons, creating a faint, diffuse luminescence exactly where the zodiacal light appears. Then there's the wild card, electromagnetic mirrors in space. Solar wind particles energized by the sun's magnetic field could be exciting sparse hydrogen atoms in ways we don't fully understand, producing a self-sustaining glow. Or perhaps the dust isn't missing at all, just hiding in plain sight. Recent observations hint that much of it might be locked in fluffy, fractal-like structures, so porous they're nearly invisible to detectors but still reflective enough to scatter light. The deeper we dig, the weirder it gets. Some researchers argue the excess glow isn't coming from our solar system at all, but from a vast, unseen reservoir of dust in the outer solar system, illuminated by a still undetected interstellar light source. Others wonder if we're witnessing the slow disintegration of a primordial Kuiper belt object, its remains spreading like glitter across the ecliptic. Whatever the answer, the zodiacal light isn't just a pretty sky show. It's a cosmic crime scene, and we're still gathering clues. Every unexplained photon is a whisper from the universe, hinting at forces or particles we've yet to discover. And that's the real magic of anomalies. They're not just gaps in our knowledge. They're invitations to look deeper, think wilder, and remember that even the simplest glow might be the first clue to rewriting the rules. Gamma-ray bursts are the universe's most violent fireworks explosions, so bright they outshine galaxies, flaring for mere seconds before vanishing into cosmic history. But buried in their fleeting light is a glitch that's shaking the foundations of modern physics. Some bursts arrive with their highest energy photons delayed by mere milliseconds compared to their lower energy counterparts. According to Einstein, all light should race through the void at the same speed. So why are these cosmic speedsters stumbling at the finish line? This tiny discrepancy, dubbed the time lag anomaly, might seem insignificant. But in the realm of relativity, where the speed of light is the universe's ultimate speed limit, even a millisecond's lag is a screaming red flag. One leading explanation dips into the speculative world of quantum foam, a frothy, turbulent texture theorized to exist at scales 1 trillion times smaller than an atom. If spacetime isn't perfectly smooth but instead churns with microscopic fluctuations, high-energy photons could interact with this foam more strongly, slowing ever so slightly like a hiker trudging through thick mud. It's a radical idea, suggesting that even the vacuum of space isn't truly empty but seething with invisible structure. Then there's the extra-dimensional angle. String theory proposes hidden spatial dimensions curled up too tightly for us to perceive. But what if gamma rays occasionally leak into these dimensions, taking scenic routes through higher geometry before rejoining our familiar three-dimensional world? This detour could introduce just enough lag to explain the anomaly. Imagine two cars leaving a city at the same time, one taking the highway, the other ducking through back streets. They'll arrive at different times, even if their engines are equally powerful. But skeptics aren't ready to rewrite physics just yet. Alternative explanations point to more mundane causes, like internal processes within the bursts themselves. Perhaps high-energy photons are emitted slightly later in the explosion's chaotic chain reaction, or interstellar dust scatters certain wavelengths more than others. The challenge: gamma-ray bursts are so far away, billions of light-years, that untangling these effects is like diagnosing a distant car crash by the sound of its echo. The stakes are cosmic. If the time lag anomaly holds up, it could be our first experimental whiff of quantum gravity, a bridge between Einstein's relativity and the probabilistic quirks of the quantum world. New telescopes like the Cherenkov Telescope Array are now hunting for these delays with unprecedented precision, turning gamma-ray bursts into cosmic stopwatches. Whether the answer lies in foam, hidden dimensions, or something even stranger, one thing's clear: the universe loves to flirt with the impossible, leaving us to decode its whispers 1 millisecond at a time. From the wow signal's tantalizing whisper to the cosmic ledger of missing baryons, we've journeyed through 25 of the universe's most bewildering glitches, anomalies that don't just bend the rules of reality, but snap them in half. These aren't mere gaps in our understanding, they're blazing signposts pointing toward frontiers we've yet to map, Black holes that shouldn't lose information, voids that shouldn't be so empty, spacecraft that shouldn't slow down. Each one is a crack in the facade of our knowledge, and through those cracks the cosmos winks at us with mischief. What ties these puzzles together isn't just their strangeness, but what they reveal about science itself. True discovery doesn't happen when the pieces fit neatly. It erupts from the clashes, the contradictions, the moments when the data stares back at us and says, "Think harder." Dark matter and dark energy aren't just placeholders for ignorance. They're proof that the universe is richer, wilder, and more inventive than our textbooks dared suggest. The very fact that we can measure the Hubble tension, that we can spot a millisecond lag in gamma rays across billions of light years, shows how far we've come. Yet the anomalies remind us how much farther there is to go. This is where the real adventure begins. Every unexplained signal, every mismatch in the math is an invitation to build better telescopes, to dream up bolder theories, to question assumptions we didn't even realize we'd made. Maybe one of you watching will be the one to crack Tabby's star's dimming patterns, or to find the particle that makes dark matter tangible. Or perhaps the answer lies in a principle we haven't imagined yet, lurking just beyond the edge of our equations. So keep looking up, stay relentlessly curious. The universe isn't just stranger than we suppose, it's stranger than we can suppose, and that's what makes it worth exploring. Drop a comment below. Which of these anomalies hooked you? The hexagonal storm, the great attractor's pull, the eerie silence behind the Fermi Paradox. The conversation doesn't end here, it's just getting started. After all, the next cosmic revelation might be hiding in plain sight, waiting for someone like you to connect the dots. The anomalies are the universe's way of keeping the game interesting. Let's play.